Okay, we are now recording. Um, just as a formality, if anybody doesn't want to be recorded, please let me know. But everybody just has to be informed. Everybody is free to speak up and ask questions if they want to as well, or ask them in text chat. This is meant to be informal, so feel free to jump in and ask questions or whatever during the course of it. You're free to interrupt me at any time. Otherwise, I'm just going to ramble. It's what I do. So this will hopefully be more interesting than last week's. This is part three. So part one, we kind of did the basics, right? We got a puzzle in here, and we made it just in the nick of time so that we could actually move those pieces around. We can just grab our pieces out here, right, and move them around. We talked a lot about sort of optimizing that rather than having one script for each one, having a single script that manages the whole thing. And then the second part, we went into all the networking, which was, I'm told, pretty dry, but that's unfortunately necessary. Like, it's a multi-user experience. If we were doing a single user experience, we could have, skipped all of that. But if we want it to work so that, like, when I'm dragging a piece around, everybody else sees me dragging that piece around and we can collaboratively build the puzzle, then we got to have the networking part. Yeah, I know that part's more intense. It's not as visual. It's not as interesting to look at, and it's more cerebral. But it has to be done. But this time, part three, we're hoping to get back to some more of the visual stuff. We obviously are still going to be doing a lot of code here, but we're hopefully should be doing more back and forth between the code and Unity, because our goal this time is kind of map out how the pieces all connect to each other and make it possible to randomize the puzzle and then snap the pieces back together. So we'll be experimenting with that as we go in real time. And there will be some code heavy parts of that, especially up front, to kind of map all that out, because every piece has to know every other piece that it connects to, what all of the four pieces are around it. And so we kind of have to preload a bunch of information about every piece so that when we're moving them around, they have what they need available to them. And we talked about a little bit last time how, even though these pieces are all kind of cut out differently, like, these are not straight lines and they have different connections with each other, it is functionally a grid. Like, these are rows and columns, and that's actually going to simplify our work quite a bit here, is if we just think about this as a certain number of rows and a certain number of columns. We're just building kind of a matrix out of it. Not exactly a matrix, because we're going to basically build relationships between all of these pieces, but it is a grid. So what we're going to do is we're just going to jump out of play mode here, and we are going to come over here to our main puzzle script. We talked a little bit the first time we did this. We made ourselves a little C# script. We just called it Puzzle Preparer, and this let us take a puzzle that had been exported from Blender and just run a tool on it that made it usable for us in a way that made sense for our puzzle game. So when we first pulled the puzzle out, it was just a bunch of pieces, and we have this tool that takes all those pieces, reparents them inside of puzzle piece one, puzzle piece two, and so forth. And that way, when we're dragging pieces around, we're actually dragging the parent around and not the individual piece, which will become increasingly important later. We may look at that puzzle script again, because there's some additional setup that could be done on this to kind of make things easier as we go along. But let's just focus on the relationship to start off with, and see where that takes us. So we've got our main puzzle script, our main server script here. It's the networking we did last time. And our puzzle script, the first thing our puzzle script does when it starts up is it looks at every piece that it has, and it builds a big table out of all of those pieces, where they are, what their ID is, where they started, things like that. And so what we want to add to this is we want to add the relationships to this. And in order to do that, one of the things we're going to need to do is be able to tell it how big the puzzle is. So we have I think we added this up here, just puzzle size 12 last time. And that is, I think we went by 2, 3, 4, 5, 6, 7. Yeah, so that's just the number of rows, basically, because these are in here by row instead of by column. You can see as I go down this list that I'm going up row by row. So that means that using the puzzle size variable, we know that every 12 pieces that we go starts a new column, basically. And whether you think of these columns or rows doesn't really matter, because you can think of it this way. If it were a portrait puzzle, it's just how many iterations over the children before I have to move to a new set. So we've got puzzle size. We're going to go down here to our puzzle info, and we're going to say that we're going to start a new just call it relationships. Start a new table called relationships, right? And this is going to be the 4 possible ways that this puzzle piece can connect to other puzzle pieces, right? So we've got top, bottom, left, right. What we call these doesn't really matter as long as we keep them consistent. And then we have to decide whether this piece has all of those, right? Because some pieces, like edge pieces and corner pieces, aren't necessarily going to have a full set of relationships. So like puzzle piece 1 only has 2 relationships. It's a corner piece. And puzzle piece 2 has 3 relationships, but it doesn't have anything on the left side of it. So not everything is going to make sense that way. I think what we're going to do here is we'll just actually do our relationship building in a whole separate loop here. And that way we have all of our initial table assumptions in place. So rather than iterating over the pieces, we're going to iterate over puzzle info here. So let's put this down here. And this is going to be, it's going to be puzzle info. And inside here, we can say, all right, well, we need to figure out which row we're on. So we are going to make a new variable just called row. And this is actually just going to be P divided by puzzle size, right? So we know how big of a puzzle we are. And so if we're on, and this actually is going to be an integer. So it's if we look at this is all 1 based. So puzzle 1 divided by 12 is going to be 0. 12 doesn't go into 1. Puzzle divided by 2, by 3, by 4, all of these up until we get to 12 are going to be row 0 effectively, because that number, like 9 divided by 12, actually comes out to be 0. But 12 divided by 12 comes out to be 1. So this guy would actually be misplaced if we weren't careful. It would think 12 divided by 12 is actually the next row. So what we actually want to do, because this is 1 based instead of 0 based, is row is actually P minus 1 divided by puzzle size. In a 0 based language, that minus 1 wouldn't be necessary, but because this is a 1 based language, things are kind of have to make some little bit of accounting changes there. So that's going to be useful info for us. And there's Richie. So we're just going to go here and just say, okay, well, now how do we determine relationships? Well, for the relationship of the one puzzle piece that we're on, if we think of the puzzle as this being upright, then the piece that is its top relationship is always going to be the next piece down, right? So it's whatever its index plus 1. 1 plus 2, 1 plus 1 is 2, that's this guy. 2 plus 1 is 3, that's this guy. We're always incrementing the index to get the top relationship. So as long as we haven't hit an edge, then our relationships dot top should be p plus 1, right? Um, Theoretically, the opposite is true for relationships dot bottom, right? That should be p minus 1, right? So every time we want to find out what's below them, we're actually going down the list. That's just kind of confusing because we're scrolling up the list, but the number is going down. So 7, if we want to find out who's connected on the bottom, that's 6. We're going down 1. And then things get a little trickier when you start looking at like, okay, what is the relationship to my left and to my right, right? So relationships dot left, if we look at this, well, that's actually the same index, but in a row over, right? So theoretically, this would be whatever P is minus puzzle size, right? Because puzzle size tells us how big each row is. So if we're on piece 16, for example, and we want to find out the piece to the left of that, then we need to subtract 12 from it, and that would give us 4. And the puzzle size is 12 because 12 is how many pieces are in each row. So we're just subtracting a whole row. And then for the other side, obviously, if we're going the other direction, the opposite is true, right? We're adding a whole row to get the right connection. So we're adding P plus puzzle size there. So if I'm on P16 and I want to get to the piece that's next to it, that's 16 plus 12. It's 16 plus one whole row, so that's 28. We just that will define the relationship that this piece has to those around it. Now, of course, that's still making the assumption that every piece has that many relationships, right? So we can kind of do some quick sanity checking here, right? For example, we can say if relationships dot left is less than 1, then that's not real, right? Then we'll just say that, and we can actually do this before we initialize it if we wanted to. We can say if P minus puzzle size is greater than or equal to 1, right? So we're not less than 0. It's a valid index because our index ranges from 1 to 192. So anything that's not within 1 or 192 isn't a real piece. And so we will just leave that relationship undefined in that case. And the only time that should happen for left side pieces is on the very leftmost row. Because if I'm here and I do 12 minus 12, that's going to be 0. If I do 1 minus 12, that's going to be negative 11. Like those numbers don't make any sense. So for this first row, anytime you take those numbers and subtract 12, then you're going to get 0 or less. And so we want to ignore that relationship. The same thing is true on in the other direction. We're defining the right relationship. Well, what if we have a right edge piece? That's the opposite problem. We know there's only 192 pieces, and so anytime that our assumptive index is over 192, then that's not a real piece. So we can say if P plus puzzle size, it keeps wanting to autofill the wrong variable in here, is greater than all known puzzle pieces. Well, actually in this case, we wanted it to be less than or equal to all known puzzle pieces, then we can define a right relationship. Otherwise, we leave right undefined. There is no relationship there. And then we have to look at the top and the bottom, which are a little bit more convoluted because the tops and the bottoms are still valid indexes, right? So if I look at like um, 24, that's in the middle. There's still an index before it and an index after it. There's a 23 and a 25. But visually, there's nothing above that. And so we need to treat that as if it's kind of the end of its own unique set there. So how do we do that? Well, for top to not have a top, um, it must be the highest numbered piece on its row, right? Because we're starting from the bottom and we're working our way up. So all the pieces that don't have an upper piece are the highest numbered piece. 12 does not have a top. 24 does not have a top. Those are the top pieces of their row. 36 does not have a top, and so forth. So really, this is about where this piece fits in their row size. So if we just kind of puzzle out the math on this, then we can say if P modulus puzzle size, right? So that's going to give us the remainder of, the remainder after we divide it by puzzle size. So if we have 7 modulus 12, that's going to come back as 5. That's not the end. If we have 11 modulus 12, it's going to come back as 1. That's not the end. If we have 12 modulus 12, that's going to come back as 0. There's no remainder, so it must be the last piece in its set, right? So if basically if modulus puzzle size does not equal 0, then we should have a top relationship. We're not the topmost piece in any row. It doesn't even matter which row. We're not the topmost piece in any row, so we should have some kind of relationship with the piece above us. And then kind of something similar is true on the bottom, right? We know that the bottom pieces are always the first ones in their row. It's 1, it's 13, right? So we can do basically the same thing. We can say if the modulus of puzzle size isn't 1, right? Then this has a bottom relationship. So 1 modulus 12 is going to come back as 1. 12 goes into it 0 times with 1 remainder. 13 modulus 12 is also going to come back with it 1. 12 goes into 13 one time with 1 remainder. So anytime that we have 1 remainder after dividing that by the size of the of each row, then we know that's a bottom piece. And anytime we have 0 remainder, we know that's a top piece. So this means that by doing this, then we've excluded all edges and corners from having defined relationships with the pieces around them. But anybody who is not an edge or a corner will have a 4-way relationship. And then we just need to make sure that we save this information. So we're just going to save it into puzzle info p dot relationships. Relationships is a bit of a mouthful, but what we'll do is we'll just call it connections equals our relationships table. And then just to make sure we don't run out our frame time here, we'll make sure we put a yield in here just in case we end up with a very large puzzle that's trying to do too much on one frame. So on startup, we look at every piece, we catalog every piece in our puzzle info table. We have what's your ID, what's your container, where did you start, that sort of thing. And then we are then building a relationship of like, who do we belong to? Now, this is a good start. It tells us whether we should connect to people on any one side, and it also tells us the index of that connection. So if I wanted to know who a piece connected to, then I would look at puzzle info relationships dot top to get more information about that specific piece that it's connected to. So this is good. We have an index, but we need more information than that to build on. Um, all these pieces are sort of different sizes, which means they start in different places. Even though this is sort of a grid, right? Every piece has a four-way connection. The pieces are all sort of different sizes. They don't necessarily have, they're not, the pieces are not necessarily lined up in a row. If we look at these, we can see that like their positions, if you look up on the upper right here as I go through these, their positions are a little bit unpredictable. They're kind of random numbers. Their offsets are a little bit different from each other because they're all sorts of different shapes. So if we want these pieces to fit together properly, then we're going to have to remember not just who was to my left, but how far away from that guy I was. What is my offset from him to the left side of him instead? And that offset can be not just side to side, but vertical, right? It's a two-dimensional offset. All these pieces are flat. They're on the same vertical plane. What does the hash sign do? The hash sign is just count how many pieces. So this just, if I say uh, hash puzzle info, that's saying how many entries are in the puzzle table. And we know that because we looped through all of the possible children before and every children got put into the table, the number of entries in that table should be the same as the number of children the object had, which is the number of pieces that the puzzle has. And so this is just saying this is a 192 piece puzzle, so this loop is going to go 192 times and look at all 192 pieces. You can do that with strings too. You can do hashtag string and find out how long the string is. It's just Lua, tell me how big this thing is. So offsets, we're going to have to figure that out. Um, so what we're going to do here then is we're going to make these relationships more complicated rather than doing just top equals an index. Then what we're going to do is we're going to make each of these a subtable, and we're going to say they have an index, but then they also have to remember an offset. But that'll have to be defined further down. I'm just showing you here for an example. This is what these are going to look like. There's going to be one of these for all of these, right? All of these will need both an index and an offset to them. If there's no relationship to define, we're still going to leave them as nil, but that's what we're doing down here. So when I'm making top, instead of just assigning it a number, what I'm going to do is index offset. How do we find the offset? Well, the offset is going to be the difference between my container and the other guy's container. So we have that information. We're going to, well, we can do the calculation twice, or we can just do it. We can just do it here. We'll simplify it later. I know how to get my position as a piece. My position is puzzle info p dot container, and we're going to go based on local position. Probably makes the most sense. And then I need to subtract that from the container of the other guy. So who is the other guy? The other guy is p+1. So whatever piece I'm currently looking at in the loop, which is P, take my position and subtract it from who I've decided is my top relationship. Take that same index that we're putting over here and we're getting that index out of puzzle info and getting his container, his local position. That's going to give us 2 position vectors. Subtract those, we get a new vector that is the difference between those vectors. That's our going to be our XZ offset from them. And we just need to do that for all of these. So this one is P minus 1 in both places, right? That's going to give us our offset. This one is P minus puzzle size in both places. And this one is P plus puzzle size in both places. All right, so that's a lot, but it's something that we can work with. So if we want to kind of see how that works, this is enough information where we can go, all right, since we now remember everyone's starting location and everyone's relationship, we could destroy the puzzle now and be able to put it back together. So let's just make ourselves a little function here that's going to take the whole puzzle apart and just kind of randomize it all together. What we're going to do with that is, let's just start with something simple here. We're going to make a new function, randomize the puzzle, right? And we will just, once we get done with all of our setup, then we're going to call space.host.invoke delayed, randomize the puzzle. Yeah, wait 1 second, randomize the puzzle. So we'll just have it, we'll have to be like, you catalog the whole puzzle, randomize it now. So we're looking at a 192 piece puzzle. We want it not to be together anymore so that we can put it back together. How do we do that? Well, we can just sort of put pieces just literally randomly. We can do that as kind of a first step. It's not there's problems with that, but like you're going to end up with a lot of pieces that are overlapping, things like that. But it's a starting point. So, like, what if we say just loop through all of our known pieces. Puzzle info we're going to be referring to a lot. That's all the pieces that we know about, all the data we've collected about all of our pieces. And then we're just going to scatter them around. We know where our main puzzle is, right? It's like we've got a puzzle like container object. It's over here in the corner, which is probably not the best place for it. But if we know that it's in the corner, then that's fine. We can work off of that. I don't know why it's under the ground, but this has got a ½ meter offset. Probably doesn't really matter, but just kind of cleans things up a little bit, makes things a little bit easier. All right, so we know that our puzzle's over there, and so we can kind of define like how big we want the scattering to be, how big of a mess do we want to make on this. So let's just do this. Let's just say that for every piece in our puzzle, that's puzzle info p dot container is the actual thing that we want to move around, because all of these pieces are in, because like there's the piece, but then that's inside of a container object called puzzle piece 1, puzzle piece 2, etc. Sorry, what's that? I wasn't sure if that was meant for me or not. Anyway, I guess not. So so that's our container object, and what we're going to do is we're just going to randomize its local position, right? So we're going to make a new vector. Positions are always vectors, and what we're just going to do is we've got space.math.random range, right? So if we look at our scripting library, we've got somewhere in here, where's it? Library, math, right? So we can do random numbers, we can do ranges of random numbers, random integers. We want random range because we want floats, not integers, right? Because positions have more precision than just an integer. And so what we're gonna do is we're gonna do random range there, um, something between nothing and let's see, this is so all of these pieces are, oh, actually, you're in the middle. Let's use that container object instead. That's fine. So if this is in the middle, then we're going to have a negative to positive randomization on both sides. So let's say that we want somewhere between a 4-meter variance, so between -2 and +2. So what we're going to do is we're going to say somewhere between -2.0 and a +2.0 variance on this axis. Nothing on this axis, that's the vertical axis, right? Y is up and down. We don't want the pieces to scatter up and down. We only want them to scatter side to side. So we're just going to scatter them on the X and the Z axis. Too many parentheses there. All right. And let's see what that does. 2 meters may be way too much or way too little here, but if we run this, make sure that our relationship catalog didn't break anything, and then the pieces all kind of run into a problem. Oh, used too many cycles. So you can see it started randomizing the puzzle but didn't finish, and that's because it was trying to do too much on a single frame. So that just means our randomized puzzle needs to be a coroutine, right? And fun fact, invoke delayed actually is the same thing as starting a coroutine. If you say invoke delayed 1, for our purposes, that just starts a coroutine that has a 1-second yield at the beginning and then goes on with it. But let's explicitly define it as a coroutine. And then we just need to put some yields in here. We're just going to do the same thing we did here, where if we're trying to scatter too many pieces, we're not doing a lot on this, so we can afford to scatter more than 10 at a time. Let's say we're going to do 50 at a time. And then if we have more than that, we're going to take a break. And our whole puzzle got jumbled up. And it turns out 2 meters plus and minus is actually just about the exact size of the original puzzle. So we probably want a little bit more scattering than that, but you can kind of see that like each piece randomized with no sort of awareness of the pieces around it. And so you end up with a lot of pieces that are overlapping. You can mitigate that a bit by, for starters, increasing the randomization range. So that'll just naturally lead to less overlap. But if you really want all the pieces to be scattered in a way where they're all visible and no overlap is happening, then you would have to do some additional checks. You're like, okay, I'm gonna move this piece to this new spot, but first I'm gonna pick a spot and be like, okay, is that near anything else? If it is, then I'm going to pick a new random spot or move it around a bit. But you can see just that by increasing the scatter range from -2 +2 to -4 +4, we just sort of naturally, organically have way less overlap just because there's so much more space to spread out. There's less chance of a random collision. So we're not going to dig too deeply into that. This is something that we can improve upon later. If we want to, we can make the scattering better. But for now, we just want it to be scattery, right? We can still grab all these pieces now that they've been scattered, move them around. That still works. That's fine. So we're making a little bit of progress here. And this scatters in a square, right? If you decide, like, oh, the original puzzle wasn't a square, it was a rectangle. I want it to be a little bit more rectangular, then, scatter in sort of a rectangle. Then just, we can, for example, make the x-axis 5 and the z-axis 3. We don't have to scatter the same amount on each axis. And then the puzzle is going to be spread out more like you kind of imagine it to be. It's a landscape puzzle, so you kind of expect the pieces to be spread out in a similar landscape fashion. So we have that now. Just a little tweak here, it just kind of makes it look a little bit more natural. But like I said, we'll worry about the collisions later. Did somebody have a
Question,
question?
Josh.
Yeah.
Yeah, can you hear me?
Yes.
Yeah, okay. Could you allow for the size of the original rectangle shape and put the pieces outside of that so you've got a clear area to start again? Because where would you actually start putting your piece without having to sort of move every single one of those out of the area? What I'm thinking is if instead of the randomized -5, you did a, I don't know, a -2 and then randomize another plus another
Yeah.
figure
Absolutely.
on there to allow for it to form a rectangle in the center that's clear.
Yeah, absolutely, you can do that. Um,
Yeah, good.
and there's no right or wrong answer to that. That's kind of a preference, and that's something that, like, if you wanted to, you could make it an option on the game and let people decide how it gets randomized. Because there's nothing that stops you from looking at this and going, oh well, I can kind of see these pieces connect and start building clusters inside of this, right? That's one way people do a puzzle, just dump all the pieces out and then start building clusters. If you want to scatter all the pieces completely out of your way and have an open surface to work with instead, then yeah, you were on the right track there. So if we wanted to do that, um, we could scatter them all off to one side. If we want to scatter them around, then we kind of have to cut a hole in the middle of it. So you would do something like, um, instead of doing this, you would say like, okay, I want you somewhere between 4 and 5 meters away from the center of the board on the x-axis. But because we want it to randomize from side to side, um, then you could do something like that, where what is randomizing it side to side? It's a bit flip, right? It just means if I'm going on one side, it's a positive number. If I'm going on the other side, it's a negative number, right? That's the only difference between whether that piece is going to go to the left side or the right side. And so you can do something where you say, um, whatever the random distance is, we want to multiply it by a random bit flip. And so what we would just do there is like space dot math dot random integer instead, right? We have both of those options. But then what I'm going to do for that is, um, this may sound a little weird, but you can do something. If what we want is like randomly having a one or randomly having um, a -1, right? And so we could do, if we did -1 to 1. The problem with that is that you could potentially come up with a 0 in the middle of it, right? And then
Yeah,
that would
yeah.
just zero out this, and that would just be nothing. It was just a piece would just show up in the center of the board. Um, so, um, well, yeah, it's what we can do here is just you can kind of fake it with, if you do negative, if you do like 0 to 1, and that could potentially result in a 0 too. Um, yeah, it's one of those things that
Bit of
sound
a,
that
it
sounds
can be
simple.
done, I'm sure, but yeah.
Sounds simple, but then you got to work out the math for it, because like I said, all you want is a random bit flip. And there's a couple. There's obvious ways to do this where it's more convoluted. It's doing it inline that can make it more difficult. For example, if you were to write all of this out, if you could say like, um, explain it as like make a new variable. Where is the new position going to be? That's just going to be like, we're just going to start it off as like no offset, right? So that's just going to be vector 0. Vector 0 is just a vector that's 0, 0, 0, right? And then we're going to say if space dot math dot random range is going to be between 0 and 1.0, and what we're looking for is like a roughly even chance. So we're going to say
Yeah.
if this comes up as higher than 0.5, we're going to do one thing. If it comes up as lower than 0.5, then we're going to do something else, right? And so
Yeah.
on this one, we would be saying, okay, well, in that case, puzzle or new position dot. Are you sorry? Did you guys turn your microphone on to ask a question, or I think they just keep
I
turning
No,
their
think that was
microphone on.
Christoph.
But yeah.
yeah.
So we could say in this case, if it's over 50, we want to go on one side, and that's going to be positive. If it's under 50, then we're going to a different side, and that's going to be negative, right? And we're
Mm-hmm.
doing that
Mm-hmm.
for both pieces, right? We're doing that and because we don't want to tie those two together. We don't want X and Y to both have the same random determination. So this is, and then down here, we would just say this is equal to new position, right? And so
Yeah.
this should give us, if we go over here and play this, well, that went to all the four corners, but it left a, why did you do that? Random range between 4 and 5. Why did you all go to? Oh, they're just not randomized enough, right? Like they're in piles, but
Yeah.
they're just not randomized enough.
I'd
So
say
what,
your 4 and 5 isn't high enough, is it? I think maybe the 3 and 5 or 3 and 6 or something
yeah, so like
instead of 4 and 5.
on this one we might do like 2 to 5, and on if we make these see we wanted it to be wider on one side, so this might be like 2 to 4, and then this one might be like 3 to
Yeah.
5. So you can play with the numbers here. So we're actually just making little piles there, um,
Yeah.
which is not exactly the effect that we're going for. But the reason the reason for that is that we're just doing um, it's we're treating it as always
What
being.
what if you what if you left the same mechanism in but did a kind of an offset addition at the beginning before the
Yeah,
random? So it
the
definitely and then make the random range bigger sort of thing.
yeah, the problem is we're not treating this as an exclusion in the middle, right? We're treating this as two separate exclusions, a horizontal and a vertical exclusion. So it's actually filling in the
Ah, yeah,
corners
yeah,
between those exclusions. So there's a lot of
yeah.
different ways to scatter these around. But we could spend all day on scattering here, but we want to get to the connecting the pieces. So
Yeah,
um,
I'll shut up.
let's do that. But yes, you can have more intelligent scattering mechanisms here and kind of figure out what that looks like. So we'll just leave that
Right.
as it is for now, but we can refine the scattering on that later. Um, so the next part then, let's see, we got like 40 minutes left. We'll see what we can do here. The next part on that is going to be when I'm dragging a piece around, regardless of where it started, I need to know whether two pieces connect to each other. We have a little bit of a bug here with our networking code. Lets us move each piece one time, and then I can't pick that piece up after that. So we have a little bit of a networking bug that's carrying over from part two here. Puzzle script, puzzle server script. Why are you not letting go of the piece when I'm releasing the piece? That piece going to everyone. Where is the message? Is it piece released. Yeah, piece released. It still thinks that it's not coming to me. We may have to figure that one out here. Space.log, and then we're just going to server message, JSON serialize data. Let's put that here and see what we're getting back from the server. So that's piece claimed, piece released, but then it still says we are getting piece released ID 192. So this should be, yeah, ID 192 is going to nil. So why do you still think I'm moving it? Clicked piece is 192. Let's make sure I'm actually piece clicked. And what is clicked piece.id? Sorry, we have I'm not going to spend much time on this because it's not going to actually stop us from going much further. I may debug this later, but let's just see if it's something easy. That's piece 92, and I'll let it go. Piece 92. Okay, something, for some reason, it thinks we're still moving pieces when we're not, which should not be the case. Piece released, piece dragged. Well, let's just see what it thinks. I mean, it's got to be me, right? Because I'm the only person in the scene. Then that's going to be, instead of saying by someone else, I can say by, who do I think is moving that piece? Yeah, well, that makes sense, but I don't know why you think I'm moving the piece when I'm not. So move it once, and then we're getting, let's see, it's uncollapsed this. Are we getting any weird? Nope, piece released is the last one. Piece claimed, piece released. Well, that's weird. That looks like it should all be doing exactly the right thing, but apparently it isn't. Let's just make sure this is, yep, that's the same correct message. Oh, you know what it probably is? Is this coming back as, no, there's no player ID on that. Okay, we won't get bogged down into that right now. I will dig out why that's thinks we're doing that later, but we can still play with it for now. We can always just take that check out for now, and then we'll debug that later on the networking side. So let's get on to how do we detect whether we are actually going to connect two pieces together properly. And this is all pretty much going to be a big, heavy lift by our do dragging function. And so what we're going to do there is whenever we drag a piece, we are going to check whether it's near, not near one of its relationships, but near one of the offsets from its relationships. which is a little bit difficult to just explain abstractly. But let's say we're dragging our pieces around and we want to know, okay, first of all, we did the drag. We told everyone where the new place is. Now let's check if it is near anything it should connect to, right? So while we're going to do that, well, we know it has a set of relationships, and we know the ID of the object that we're dragging around. So we're going to loop through all of its relationships. So we can say, and this is something we're going to have to be a little bit careful on because it's going to take up frame time, right? And so we may decide for ourselves, like, well, maybe we don't need to check every frame. Maybe checking every half second is enough, or maybe we only check when we let it go. Maybe that's all that matters. Rather than checking that, maybe we just say when they let it go, let's see if they dropped it near something. Just because there's two different ways to do this, right? One is if we wanted to have some visual indication to the user that as they're dragging these pieces around, if they get near something, it lights up and goes, hey, you're near something that you could connect to, right? Then you would have to be checking that constantly, either every time you moved it or at least on a regular interval. Maybe every single time it moved, which is going to be, every frame, which is going to be 60 times per second. Maybe that's too much, but maybe we check once every half second if there's something around it that we need to light up or not. Then that could be a coroutine that goes every half second. Even every tenth of a second would be probably indistinguishable to the user, but less load on the system than doing it every single frame. But then, you might consider that. You might say like, oh, okay, well, that kind of makes the puzzle too easy, doesn't it? If I just drag a piece around, sooner or later something's going to light up, and I know that it connects there. Maybe that's the way you want it to work. Maybe you think that's too easy. Maybe you want to be like, you have to drop it, and when you drop it, if you drop it close enough to something that it's supposed to connect on, then we'll connect it, right? So let's look at it that way first. Let's say like, okay, we dragged it around, we let it go. Is it near something that it should potentially connect to? So let's do that here. We need to do that before we clear the dragging ID because we need the dragging ID. So check if we dropped it near a connection and then clear drag ID when done, right? So our work's going to take place in here. So we're going to loop through all of our possible connections that we could be near, right? So we're going to say start a for loop. What are our connections? Well, our connections are going to be puzzle info, dragging ID, dot connections, right? Because that's what we defined down here with all of our relationships. We have a dot connections. Every puzzle info, every puzzle piece has a connections that defines a set of relationships. And so we've got that. But if we look at this, this is actually, these relationships aren't indexes. They're associated. It's an associative array. It's a map. It's rather than just being a pure array. So what we're going to do is we're just going to, we could turn it into an array, but we can also just work with what we've got. So instead of doing this, we're going to do key value in all of the pairs that are in connections. And I don't know why I put a hashtag on there. We don't need that. We want the actual values, not the number of values. And we don't actually need, which we do. That's a function. All right. So this, instead of iterating over an array, it's like, oh, this has 10 items in it, so we're going to do 1, 2, 3, 4, 5, 6, etc. This is a non-indexed array. It's got a bunch of random information in there, but they're not in numerical order. So instead, just go through all of them still, but every time we look at one, tell me what the key is and what the value is. And so for this case, the keys are going to be top, bottom, left, right, and the values are going to be whatever table is associated with them there. And so we can say the connection point, right? We need to figure out where the connection would actually be. And that's about the offset, but it's the offset from the current location of that piece, not its original location. So we can say if, and we have a handy distance function that's built into all vectors. So we can say if the current position of the piece we just dropped, right, that's going to be puzzle info dragging ID dot container dot local position. That's where I am now. And if I get the distance from that to value, it's going to be like puzzle info value dot index dot container dot local position plus whatever puzzle info, or no, actually it's plus value dot offset. And then if that is less than some arbitrary value, we'll just make it something probably too big for now, but we'll make it half a meter. It's pretty far away, but we can tune that number later. So we're saying we're going to loop through top, bottom, left, right. We're going to look at all four of them whenever we drop a piece. And for all four of those, we are going to get the current position of the piece. Before we randomized it, we decided which four pieces were around us, but then we randomized it, and those pieces could be anywhere now. So we're saying find those pieces, figure out where they are now, find the left piece, its current position, add the offset that we expect to that left piece. That's what we're doing here, right? Because if I'm going to connect to that piece, then I was a certain distance away from it to start off with. And so it's that certain distance away that I care about, not the current position of that piece. And so I'm going to find out where the new location is for the piece that was to the left of me. If I were to connect to it, where would I have to be in order to be perfectly aligned with that piece again, wherever it is now on the table? That's what we're doing here. We're finding that new location where the piece that we just dropped should be if it were perfectly aligned with the piece that it was supposed to connect to. And then we're comparing that to where we actually are when we drop it. And we're seeing how far away we are from kind of the idealized perfect alignment and where we actually are. If that's too far away, if it's, I dropped it on the other side of the table, well, that's not a connection, right? If we make this number too small, then it'll be too fiddly, right? If we made this like a really small number, like 0.05, then the user would have to almost perfectly align the piece themselves before it got accepted by the game as being close enough. And that's just a bad user experience. You want the user to be able to roughly drag the piece about where it should be, and the game goes, yeah, that's close enough, we'll take it the rest of the way, right? So you can kind of tune that number. We're going to start it off with a wide number to start off with. And let's just say something. Let's just do something basic and be like space.log. Hey, you dropped this near its what? Its key connection, right? So we're just going to say that for now. We're not going to do anything else. We're just going to be like, hey, I think this is someplace where it could connect. So if we play this, let's see here. what I'm going to do is I'm going to put this back to, no, we'll just leave it. We'll just play it. All right, so we got all of our pieces. These blue ones are going to be really hard to identify, right? Because they're all blue. But if we look at these pieces, right, I can move these pieces around, pick it up, move it around. Nothing's happening. It's not near anything that would match up to it. So if we start, like, do these pieces go together? Apparently not quite. They kind of look like they should, but they're not quite close enough. We would kind of have to find some pieces that go together, which might be kind of time consuming for us to, because we're at this point where we're actually like, let's do the puzzle. So what we're actually going to do here is we're going to make it a little bit easier for ourselves to test this, and we're just not going to randomize the puzzle right now. So I'm just going to comment out randomizing the puzzle. And by doing that, that means that I can just pick two pieces to test with, right? So like I can grab this guy and I can drag him out here. That's cool. What if I drag the guy that was supposed to be next to him? I put it over here. I'm not getting anything in my console. That's kind of far away. But I know that this guy is supposed to be roughly right here, right? And if I zoom in here, you can see not super close, but if I look at my console, it says, hey, wait a minute, you dropped this near where its left connection would be, right? Because I knew these two pieces went together. I could drag it again, drag it over here. I'm not getting anything, probably. Oh, no, I am getting something. So that means that number is probably too low, right? If it can match a drop on the wrong side, right? How far away that's a match. Uh, yeah. So this is detecting it way too far away. If we clear this, I'm not getting anything there. Clear this. Let go of it there. That's not close enough. So we can kind of play around with it. Let go of it there. Well, that's actually not going over here. There we go. So that's actually maybe a fine number to play with for now. But you can see here it's detected that, like, okay, that's actually where it's supposed to go, right? You found the right connection, but it's not aligned, right? It's kind of where we left it. So what if we take the extra step and go like, okay, well that's you found the right spot for it, but we're going to help you out and actually finish it the rest of the way, right? So we can be like, okay, you got close enough. We're happy with that. And so what we're just going to do is we're just going to go ahead and take it the rest of the way. We're going to put it exactly where we think it should have been. See how that works out for us, assuming I got the offset on the correct side. But like if I grab this piece down here, and then I grab this piece, yep, and it just snaps right into place, right? So you can see that, like, if I grab another piece and I come down here, I'm like, that's close enough, and when I let go, it clicks into place.
Awesome. Yeah, it
Yeah.
just needs a little click noise. That'd be great.
Yeah, well, I mean, you say that, but there's actually we still got a ways to go, right? This looks like progress, and
Mm,
it is. Like, we can get pieces snapping together. They understand their relationship with each other. But
yeah.
there's questions beyond this. Like, for example, I can still grab this piece and take it out, and it just moves by itself, right? I can move it over here, and it snaps into place again.
But
Is
you
that
want to move the whole jigsaw theoretically, don't you? The interconnected bits as well.
Yeah, so that's a question. Like, for gameplay purposes, is that what we want? Is that the behavior that we want, where like the pieces get put together? But then if we decide, okay, but like this is way down here, and we want to move this whole piece that we're working on, like I want to be able to click this, and when I drag it, all of the currently connected pieces come along with it. Like, is that the behavior that we
Yeah.
want? And so there's extra work there to say like, oh, okay, well, when I'm dragging this piece, how do I drag all the pieces that are connected with it? We probably don't have time to really explore that today, but you can see that like we're making some progress here. We were able to define the relationships of it. I can put pieces in roughly the right spot, and we can play with how big that is. Like that's actually a pretty big snapping distance right there. So maybe that's too much. That doesn't snap. Oh, that's actually the wrong piece. That does not go there. That's why it's not snapping. Um, like that's probably too big of a distance. Like look how far away that snaps. We probably don't actually want the snap that big. So we might want to turn this number down to where we're looking at like, maybe zero point 0.2. Maybe that makes more sense. We have to be actually get a little bit reasonably closer. But that's just kind of dialing in the gameplay from a testing perspective when we get ready to
Just a
do
quick
that.
question,
Sure.
Josh. What would happen if you try to drop and you've got an object to the left and to the right? Is the closest going to take preference, or is it just going to snap randomly to whichever one it first finds it connects to? If there's two interconnecting pieces that you're dropping it to.
Sure. That behavior can be defined. Like, so right now, like, for example, you're talking about like, I've got both of these pieces here and they don't snap together. But what happens if I drag this piece in the middle? And technically it has a
Yeah, kind. Yeah,
relationship on both the left and the right. So
yeah,
the way the code currently is defined, it'll do both at the same time. So it's going to loop through every connection, and if it finds a connection, it's going to do. So what that means, like if I just drag this here, it appears to snap to the right. But if you look at the bottom, you can see that, oh, you dropped this near left connection and you dropped this near right connection. So what actually happened is it snapped to the left and then it snapped to the right again. So whichever
gotcha.
one is the last relationship in the loop that it matches is the one that would it connect to.
Okay.
You can redefine that, right? You can say as soon as you snap to any one of these, stop looking.
Yeah,
Whatever the first one is, instead of whatever the last one is, whatever the first connection we make is, break, and that
yeah,
break is going to abort this loop, right? So if I come
yeah,
over
yeah,
here and I play this again, and I set up the same scenario, right? I come down here and I say, take these two pieces, right? And I drag this piece in the middle of them. Previously, this snapped right because that was the last one. But when I let go of it this time, it
mm,
snaps left because that was the first match that it found. And then, of course, I can move this one
right.
to snap it as well. So you can kind of decide
Yeah,
what that is. And um, if you wanted to, you could do both, right?
yeah,
You could say, I dropped this piece and I've detected that it has a matching connection on both the left and the right that it should fit into. And so what I'm going to do is I'm going to snap this piece left, but then I know which piece it also had on the right. So I'm going to go get that piece now and snap it in next. Pretend that basically just auto move the other piece on behalf of the player. So because like right now that would
yeah,
basically be
yeah,
doing like if I have these two pieces and I move a piece in the middle, it snaps left, but then
yeah,
this piece sits here. But if I pick this piece up, then it's going to snap into place too because it's in the right spot.
yeah,
So you could
yeah,
just emulate the player doing that, going like, oh, I know you dropped it next to multiple connections, so I'm just going to automatically connect all of them together. That's a little bit more complicated.
yeah,
There'd be more logic behind doing that. But
yeah,
you can iterate on it. You can build on that. The simplest version, which is still very understandable to players, right? If I have these pieces here, I'd be like, oh, I drop it in here, it snaps to one of them. Okay, I'll snap the other one now. Like that's not
yeah. That's the more logical way.
it's
Yeah,
not a big burden on the player, and generally, you want to avoid moving pieces on behalf of the player. And if you were going to do that, where you auto snapped other pieces, it gets a little bit more complicated with the networking because you first have to make sure that
yeah.
nobody else is already trying to move this piece before you decide to auto snap it in place. So you have
Or
to
try to move out any of it, or to try and move out any of the interconnected pieces. Any player could be randomly doing that as well, breaking the link.
I
Yeah.
just thought of another problem that's going to come up in a second, and that's now you've got two little groups there. How do you move one
Ah,
group to the next group?
Yeah.
that's
So
when you're going to be able to pick the whole lot up. That's a reason to have to be able to pick the whole lot up, isn't it?
yeah, I mean,
Yeah,
I could manually go, okay, well, I see these two are the same, so I'm going to move all these pieces up here one at a time. But that's kind of a
Yeah,
pain, right?
yeah,
What we'd really like to be able to do is like drag all three of these pieces at once and drop it
yeah,
in place here, and that's doable. It's not, except we don't have time to do it in the next 10 minutes, but that's something we can look at part four. Basically, how that works is we're going to define a new relationship where right now, if we look at these puzzle pieces, these pieces are all just in here. They're all siblings, right? They're they all have the same parent. Their parent is the master puzzle, and they're all just siblings with each other. But what we can
yeah,
do in the future is we can say like, okay, these guys are all siblings because they're not connected. But if I drag this piece over here and it snaps to that piece, then what I'm actually going to do is I'm actually going to parent that piece
you're
to the
going to
guy
make
I
it a
snapped it
Siamese
to.
twin, aren't you? You're going to make it a Siamese twin.
Yeah, I'd be like, oh, okay, you guys are. I'm actually gonna like, you're now a child of that other guy's container, and so when I
Yeah,
move that one container around, I'm now moving all the pieces in that container around. But that
yeah,
complicates some things. So you have to be careful when you're doing that. Like it'll complicate detecting whether like, okay, but if I move this guy over here, he's now um, a child of a different parent. So his local offset, when we're doing detection, we would actually be comparing the world positions of these instead of the local positions of these to decide whether they get
yeah,
snapped together. So that's one thing that would have to change. Um, then the other thing that would have to change is when you start dragging pieces around, like it would work as expected if I grabbed the specific piece that was the parent by chance and started moving him around. It would just look like I'm dragging the whole thing around. But what if I grab one of his children and start moving it around? That would have to be there would have to be some additional logic there. And it's not complicated. All that means is that um, when we start dragging an object around, if I grab an object, I'm first going to check to see if it's parented to something. And if it is parented to something, then I'm going to make drag object its parent instead of itself. And so then that will make it seamless where I can pick up a child. And even though I clicked on the child and I'm dragging the child around, it's actually moving the parent's container around. And then you have to get into the logic of, okay, well, what about snapping that whole group to another whole group? And that's not too difficult. What you would do is you could remember both the child object that you clicked on in addition to the parent object that you're actually moving around, and you would still just do the snapping logic based on um, the child that you actually clicked on, even though you're dragging its parent around. And so, like, if I clicked on, you know, this middle, if we had something like, if I clicked on this middle piece here and was dragging it around, um, as long as I dragged that middle piece someplace where it connected, then all of its siblings have to be good connections too, because that's a grid. That's the way it works, right? It can't be that this middle piece is a good connection, but the side pieces aren't. That doesn't make any sense, right? That would never be a thing that happens. So as long as the
yeah,
specific piece that you're dragging finds a valid connection, you can just assume all the other pieces that it's connected to also can snap cleanly into place in that same spot.
yeah,
But you have to but the logic of how pieces get moved around and detected gets a little bit more complicated when you're dragging all the pieces around. And then you have to remember to do things like, okay, if I'm snapping two objects together that are two sets, then I have to take like all of the children from one set and reparent them to the new set, rather than just snapping them into position. And when the puzzle's done, we should end up with a puzzle where everything is now under one parent because all the pieces are connected. And so when we go to re-randomize the puzzle, we're like, oh, that was fun, let's play again. And the puzzle gets randomized again. We have to break all of those children back out into being unparented children where they're all just loose siblings again and scatter them around. So there's some complexity there, but it's probably not as much as it sounds like it is. Just some bits of code have to change here and there. And that's something that we can look at for part 4. I know people probably didn't think building a puzzle was going to be 4 or 5 parts, but there's when you start getting into it and you start playing with it, then it turns out there's a lot more you have to think about than just dragging the pieces around. But we're making good progress. Like we can actually play with our puzzle now. We can scatter it around and we can put it back together. There's not a lot of rules in place yet, and we can't drag groups around, but it's kind of almost a puzzle now.
Yeah.
Yeah. Yeah, it's good.
Okay. We're going to leave it there for today. I'm going to stop recording